All right, ninth graders, we are doing arithmetic sequences as functions. This is page 75 from your math binder. Let's start with this story up here at the very top. It says, Scott has decided to add push-ups to his daily exercise routine. First of all, let's give it up for Scott. Good for him, trying to up his exercise routine. Okay, so he's keeping track of the number of push-ups that he completes in a bar graph as shown to the right, with the day one showing that he completed 3 push-ups. So we can see that here, day 1, Scott did 3 push-ups. After 4 days, Scott feels confident that he can continue this pattern of increasing his number of push-ups completed each day. So let's start by making a table of Scott's push-up progress. We know that when it was day 1, it said that Scott did 3 push-ups. So fill in the rest of the table and let's find this pattern. Push pause. Okay, so from our bar graph thing here, Scott only went to day 4, but we're still gonna put in days 5, 6, and 7. We know that on day 2, Scott did 5 push-ups. Day 3, Scott did 7 push-ups. And day 4, Scott did 9 push-ups. Now, the pattern that we see here, 3 plus 2 would give us 5, plus 2 is 7. So 9, 10, 11 would be day 5, 13 would be day 6, and then 15 would be day 7. Okay, so let's answer some of these questions. What's the domain in Scott's situation? Domain is the input. Domain always comes first. Domain is the x value. So the domain here is the number of days. And in parentheses, I'll remind us that that is the input. What's the range then? Our range is going to be the number of push-ups, and that is the output. Okay, does this situation represent a function? Does every input have exactly one output? Well, day 1 can only give 3 push-ups. Scott only did 3 push-ups, and really no matter what day it is, he can only do a single quantity of push-ups. He can't say, you know, I did 3 push-ups today, but I also did just 5 push-ups. He did 5 if he did 5, that's all. If he did 3 and then 5, then his total is 8, that's all. You can only have one total for your day. So yes, this is a function. Each day gives one amount of push-ups. So what kind of a sequence? Remember back to our growing dots. Remember, we said that if it was an adding sequence, we had a certain name. And if it was a multiplying sequence, then it had a different name. Well, this one's an adding sequence. And the name that we had for that was called arithmetic. So what is it adding every single time? Well, we said that that thing that it's adding, we called D. That was our common difference. So I'm going to say D, thing I'm adding every time, is positive 2. Now, if I had been subtracting 2, then I would say negative 2 here because you're adding a negative in order to subtract. But it was positive, so I'll leave it like this. You can make a graph of this, push pause, and, well, before you push pause, actually, go ahead, graph this thing. See if you can get your graph perfect. Push pause. Okay, so when we get this graph, this was the one thing I was gonna say. A lot of times people forget to put the labels on. So if you forgot to put the labels on, let's fix that really quick. We know our input was days, so we will put days along the x-axis. Our output is number of push-ups along the y-axis. Okay, so we know after 1 day, Scott did 3 push-ups. Remember, such a baller here, Scott. After 2 days, Scott did 5 push-ups. After 3 days, Scott did 7 push-ups. After 4 days, Scott did 9 push-ups. And then you're gonna be super tempted to connect the dots. Let's think about that. Does it make sense to connect the dots? Some of you might be saying, yeah, of course it makes sense. When you have a straight line, you connect the dots. Not necessarily true. What's the situation here? Days and push-ups. So how many push-ups have they completed at 1.5 days? Do we know if Scott's halfway through his push-ups by the middle of the day? We don't know that. Maybe he does all of his push-ups in the morning. Maybe he does all of them at night. Maybe he all day long slowly does the push-ups for 24 hours. He slowly completes 3 push-ups. Now, I don't think that that third case is actually happening. But if you connect the dots, that's what it's implying. It's saying that throughout the whole day, the push-ups are increasing. All we know is how much there is at the end of the day. And when we just know one final number, we typically don't connect the dots because it's saying these are discrete things. It happens once and then he stops. If you connect the dots, you are saying that Scott does the push-ups all day long and there are amounts of push-ups between that he slowly does all day. Not the case. Okay, so I'm going to leave mine unconnected and we are going to write an explicit equation. Now, when it says explicit, it's not talking about naughty words in a song. It's talking about a direct way to find the rule here. Kind of like when we found at T minutes during our growing dots thing. We looked for a pattern and then we wrote a rule to match that pattern. So we're going to look for a pattern right now. You are going to do lots of work over here in the margin. So be ready for this. The first thing that we are going to put in the margin, we're going to use our function notation that we discussed yesterday, and we are going to write f of 1. Okay, so the input is 1. What's the output for 1? It's 3. Okay, so then we're going to skip a little line here because I'm going to leave space to add something else later. And I want to look at f of 2. Now, before we write down 5, let's remember that it is 3 plus 2 is how we got there. Okay, all right, let's skip another little space and let's go to f of 3. Well, we took f of 2, which was 5, 3 plus 2, and we did 3 plus 2 plus 2. Okay, let's do this again. F of 4, again, we're leaving a space, was 3 plus 2 plus 2 plus 2. So that's 5, 6, 7, 8, 9 at f of 4. I'm starting to see a pattern. I hope you are too. F of 5 was 3 plus 2 plus 2 plus 2 plus 2. Okay, now we are going to take a different color. You don't have to use a different color if you don't have one, but I'm going to use pink because it makes my soul feel happy. So let's write underneath here f of 5. Now I'm going to find this stinking pattern. So f of 5, it's saying that you had your 3, but how many 2's were we adding up? 1, 2, 3, 4. Well, a simpler way to do that would be 2 times 4. 2 happens 4 times. Okay, let's go to the next one. How did f of 4 come to be? Well, we started with a 3, and then we added on 2 how many times? 1, 2, 3. So instead of saying 2 plus 2 plus 2, we can say 2 times 3. On the next one, f of 3 is equal to 3 plus 2, but instead of 3 times, it's now happening 1, 2 times. If we go up to the one before it, f of 2, that was 3 plus 2 1 time. Now I'm going to be silly. I'm going to go back to f of 1. That was 3 plus 2 0 times. Now we are looking for an overall pattern where we can see how the input gives us the output. So I'm going to take all of this beautiful work here and I'm going to draw a cute little zigzag line and I'm going to write f of n because you can put any number in there. What, if we look at these pink things, what always happens in those pink equations? It always started with a 3. And then it always had a plus 2, and it always had parentheses. But the number inside those parentheses changed. But how does that number relate to the first number in parentheses? So when the input was 5, over here we put a 4. When the input was 4, over here we multiplied by 3. When the input was 3, we multiplied by 2. So it's always 1 less. So if this is n, I need to go 1 less than n. I need to say n take away 1. Whoa. Some of you might be thinking, okay, Miss Johnson, that was a lot of work. I see where you went, but I don't think I could have done that on my own. That's okay. I didn't ask you to do that on your own. I wanted you to follow so you can see how mathematicians come up with these insane rules. They look for patterns. That's literally all they're doing. So someone at one point found this pattern and they said, here's our explicit equation. F of n equals 3 plus 2 times n minus 1. Okay, so let's do a little bit of distribution. This needs to be distributed to everything inside the parentheses. So this is really f of n equals 3, and then 2 times n is 2n. 2 times negative 1 is minus 2. All right, let's combine some like terms. 3 minus 2. So I've got f of n equals 2n plus 1. Now that is our explicit equation. Why is that equation helpful? Well, before, to find any one of Scott's number of push-ups on his day, we had to add 2 to all the ones before it. Now, let's do a little bit of math. If I were going to find day 7, I could do 2 times 7 plus 1. So 2 times 7 plus 1. And I know that Scott did 15 push-ups on day 7, which I already knew, but I was just double checking to show you it works. Let's figure out how many push-ups Scott does after 2 months, which would be about 60 days. We would do 2 times 60 plus 1, 121 push-ups. Do you think Scott could do that? Maybe. Okay, so after 2 months, Scott's doing 121 push-ups. Let's find after 1 year how many push-ups Scott's doing. So we're going to say 2 times 365, that's the number of days in a year, plus 1. 731 push-ups. Can you imagine how muscular Scott would look after doing 731 push-ups in a single day? Wow. Is this feasible for now, but is it feasible long-term? I don't know. Not really, unless Scott, I don't know. I feel like if you do plus 2 push-ups for the rest of your life, you probably have a mental illness because that doesn't seem very wise. Okay, so that's an explicit equation. Explicit equations are great because they tell you any answer anywhere. So I'm going to write that over here on the side. I'm going to put a little star next to explicit, and it gives any answer. That's what's so nice about explicit equations. So I'm going to put like bubbles around it because this is a super important thing that sometimes students forget. It gives any answer. Okay, so a recursive equation is going to be a little different. One thing that you need, actually, maybe I'll start with the thought bubble first. A recursive equation gives the next answer only. So explicit is great because it can give you any answer in the entire like lineup of numbers. Recursive only can give you the next answer. So you can only use the recursive equation if you know the number before it. We would have to start at 1 and add 2 until we got to 365, and that would be recursive. So here's how recursive works. You have to know the first number in the entire sequence. That is written like this, the first number. So you would say the first number is equal to, I don't know, let's say on this one, what was the first number? How many push-ups did Scott do day 1? 3. Okay, so we would say the first number is 3, and then you'd have to tell the person what the rule is. So you would say, to get the next number, what you need to know is the number in front of it, and then you'd add 2. So it's more to help you immediately, not to help you find any answer. It only gives you the next answer. You're probably feeling a little bit confused by that. Welcome to the club. I think that it might make a little bit more sense once we go through some examples, but we are going to write down the general forms so that you have them. This is super important. You're going to want to use these forms on the test that will be coming up not anytime soon. I mean, like everything's soon and relative, but let's start by writing the explicit form. The explicit form always looks like this, f of n, and this is the one that helps you give any answer. F of n will always be the first number. Ours was 3 last time, but we would say f of 1 plus the common difference, whatever's being added, times n minus 1. Okay, write that out because we are going to put some notes with it. We are going to kind of point out this stuff. D, if you remember, is the common difference. Just going to say common diff. F of 1 is the first term. And then f of n is any term. Okay, there is our general form for arithmetic explicit equation. Let's do a general form for recursive. So you always have to start by saying f of 1 equals some number. That's your starting point. And then your second line will say f of n equals f of n minus 1 plus d. Okay, so let's explain this a little bit. Again, f of n is any term in the sequence. This right here, f of n minus 1, is the term before. And d is the difference. Okay, so we've got our any number. F of 1, that's just the first term here. And before your brain explodes from so much information, let's go through some examples. We are going to start with number 8. It says state the common difference and then write the two formulas to represent the sequence. You need an explicit formula and you need a recursive formula. So let's start by finding the pattern. How do you go from 3 to 8 to 13 to 18? If you notice here, we are always adding 5. Okay, so our common difference is going to be 5. We're going to put a positive 5 here because you're adding 5. So let's use our formula up here for explicit. F of n you keep. So we are going to say f of n. Then we've got our equal sign. What is the first term in this list of numbers? The first number in that list of numbers is the number 3. So we're going to put a 3 here. That covers this f of 1 piece. Then we're going to add the common difference. Well, what is our common difference? We just said it was 5. So we're going to say plus 5. And then this n minus 1 goes in parentheses. Now you always, always, always have to simplify. So let's distribute. And we have 3 plus 5n minus 5. When I combine like terms here, 3 and negative 5, I get negative 2. So my final answer is f of n equals, now remember we always try to move the variables to the front, so I'm going to start with 5n, and then 3 minus 5 is negative 2. So f of n equals 5n minus 2. Okay, that is our first explicit equation. I am guessing some of you, I'll put that there so it doesn't look blank. Some of you probably have some questions right now. I'm going to go through a whole nother example, but think about your questions, maybe jot them in the margins, and if you want to ask them or if you want to walk up to my desk right now, ask me. I'd be more than happy to help you. For the recursive equation, there's not really any algebra to go with it. There's not really any like actual computations. you are just going to pretty much rewrite what you see here with your information. So we're going to start with f of 1. Ninth graders, what's the first term? It's 3. Okay, then we are going to put a comma or something because we're going to separate it from the second part, just because I don't have enough space to use 2 lines. Our second part of the equation is going to be f of n equals f of n minus 1, and then plus our common difference, which was 5. Now let me interpret this for you. It says, first number is 3. To get a number, you add the last number to 5. That's all. Start at 3, add 5 every time. So if I were to follow this and not have the original, I would write down 3 plus 5 would give me 8 for the next number, plus 5 would give me 13 for the next number. I could use that to write my list. Okay, let's do another example. Let's go to problem number 9. If I look for the pattern here, it goes from 11 to 9 to 7 to 5. So how am I moving here? Well, from 11 to 9, I'm subtracting 2. From 9 to 7, I'm subtracting 2. And from 7 to 5, I'm subtracting 2. Notice I said subtracting. Here's the most common mistake that I see. People put a 2 there because they say, yeah, it's subtracting 2. You're right, it is subtracting 2. But what you just wrote is adding 2 by putting it as a positive 2. You have to remember that when there is subtraction, you've got to show it with a negative, because that says add a negative 2, which is subtracting 2. Okay, the explicit equation here. We start with f of n. Remember, I'm using this, and it equals the first term. Here, our first term was 11. And then it says plus d. Well, I could write plus negative 2, but I'm going to just simplify that to minus 2. Parentheses n minus 1. I'm following that same format as last time, but instead of 3 and 5, I've got 11 and negative 2. Let's distribute that negative 2 to everything in the parentheses. So for my second line, f of n equals 11 minus 2n, and then negative 2 times negative 1 is positive 2. When I combine 11 and 2, I get f of n equals negative 2n moves to the front. 11 plus 2 is 13. Okay, for our explicit equation, we just did our explicit equation. For the recursive equation, let's start with our first term. Our first term is 11. So I would say f of 1, or first term, is 11. And then f of n equals f of n minus 1. And plus our common difference would be plus negative 2, or I could just write minus 2. So if you're feeling confused on the common difference, let me give you a quick hint. It will always start with f of 1 equals f of 1 equals. In fact, even looking at these last two, I can see that the first term is 3. And the first term here is negative 17. That part should not be difficult. Okay, then this next part is almost always the same. It starts with f of n equals f of n minus 1. It always starts with that. F of n equals f of n minus 1. Then all you have to figure out is what's being added. So how do I go from 1 to the next on this one? From 3 to 1.5, it goes down by 1.5. 1.5 to 0, it's going down by 1.5. This is always subtracting 1.5. So I put a minus 1.5 right there. That just says it subtracts 1.5. Over here, from negative 17 up to negative 10, up to negative 3, up to 4, that is adding 7. So I put a positive 7. So put a plus 7 right there. You just finished your recursives for the whole page. I want you to push pause and to follow the format that we used on the explicit equations. Finish up numbers 10 and 11. All right, ninth graders, let's go through these last two. On number 10, we'll start with our explicit equation here, f of n equals, and we're going to put the first term in the sequence, which is 3, plus the common difference, which is negative 1.5. So I'm going to put minus 1.5, parentheses, n minus 1. Then I can distribute. I'll combine like terms. So I have f of n equals 3 minus 1.5n, and then negative 1.5 times negative 1 is actually plus 1.5. Okay, so f of n equals, I'll bring that negative 1.5n to the front, and then 3 plus 1.5 is 4.5. There is my final explicit equation. Let's go to number 11. We'll start with f of n equals first term in the sequence, which is negative 17, plus the common difference, 7, times n minus 1. I'll distribute that positive 7 to everything in the parentheses. So I have f of n equals negative 17 plus 7n minus 7. I'll combine the negative 17 and the negative 7. And when I do that, I get f of n equals 7n minus 24. All right, yes, there was a ton of work on this. I don't think these are necessarily difficult. They are just very weird to grasp at first because this is a totally new concept, writing things this way. But we're going to get more and more practice with this, but let me or your math teacher know if you have any questions on this stuff because we are more than happy to help you out.